alternative. That's the presentation he's going to do. However, he published more than 200 papers, and he has associate fellow of the American Institute for Aeronautics and Astronautics, and is also a senior review editor of Structural Multidisciplinary Universities. So the talk is there in the advertisement, and also as we do with this type of activities, we try to do technical training and also soft skills training, and the soft skills here, since he's spent his research career in the United States, he can talk a little bit about the US system, and you can ask questions. So basically, that's kind of the results. Thank you very much.
Hola. That's the only Spanish that I can speak. So please don't ask the question in Spanish. So my name is Nambo Kim, and yes. Thank you. So today I want to talk about uncertainty reduction with the data in prognostics and health management. So we are living in the era of data. Everybody's talking about data, big data, everybody's talking about data, and especially the science on that field is called the data scientist. So in this era of data, I'm a mechanical engineer, and I'm thinking about what's my position toward this era of the data scientist. If I compete with the data scientist, there's no hope that I can beat them. There must be some way that I can absorb and digest data scientists in my background. So how can I see it? And I hope that you have your own way of seeing the data. So I see the data in the perspective of uncertainty reduction. So the data to me is, I'm living with the uncertainty around me. I try to reduce them, and I use the data to reduce them. I will show you how I reduce the uncertainty with the data in my field called prognostics and health management. So prognostics is the similar to the next stage of the diagnostics. So if you smoke for 10 years, then your doctor will say, if you continue to go on, your life expectation will be such and such. That's the prognostics. I'm applying that onto the machine. So if my machine state is going degraded every day, then it will break down at some point. I don't want that actually happen, so that before the machine will break down, I will stop it and I will call the maintenance. So the question is, can I predict when my airplane will fall down from the sky? Or when my press machine will stop printing papers out of it? So that's the prognostics and health management. So I have 5 topics to talk about today. First one is the general background of what do I mean by uncertainty, especially how can I quantify it, how to propagate my uncertainty, and how to manage them. That's my background so that I want everybody to put in the same page. And then I will have 4 topics to discuss about how do I handle the data orientation, data measurement, scheduling, data management, and the physics-informed neural network. So, in my perspective or my application, when I say the prognostics, it's all about the degradation, something that works every day. So if I have an airplane, for example, if I look at some fuselage panel, if I put the sensors, and if I send the signal of land wave, then I can detect how much damage inside of the panel. And then every day when your airplane take off and landing, it has a fatigue cycle so that this damage will grow gradually. And I want to measure what's the size of my damage every flight. And then let's say this is today. And these are some measurements. So these dots, the dots are my measured crash size. Remember, I don't actually measure it. The sensor measures it. So there will be a lot of noises and errors associated with it. But that's some data that I have. This is today, and I want to propagate that trend until a certain threshold that fades, will break, and then I will predict what will happen. So that's my job. I have some data until today, and I want to predict when the dangerous things can happen in the future. Having said that, this is my airplane, but there was another airplane before me, so there are some history of other airplanes, so that I have some legacy data available until actually the failure. If you have it, that's good. If you don't have it, that's fine. So these are some available data that you can use it, and these are the data that I have currently, and this is what I want to do. And you can see there are a lot of uncertainties associated with it, so I cannot expect exactly predict what will happen in the future. So I will predict in some sense of the distribution. If you heard about the statistics for probability, this is what it is. This microphone is sensitive. If I'm here, it doesn't work. If I come here, that's good. That's good. All right. So uncertainty. What kind of uncertainty we are talking about? Koreans are very famous. I was born in Korea, and Korea is very famous about the. Have you heard about karaoke? So, I have a karaoke machine at home. So this gives me the feeling that I'm playing in front of the karaoke. So, sources of uncertainty. For example, your material, every material will have some variability in the material properties, and then your measurement data will have a noise and bias. And then the loading is the biggest source of uncertainty in many cases, especially the future loading. How do I know my airplane will experience what kind of loading in the future, right? So that's all uncertainty that I need to deal with. Among them, predicting processes has uncertainty, so we need to deal with it. So we'll talk about a lot of the distributions. So even if the measurement data comes as a single point, but in the prediction stage, we have to deal with it as a distribution. So the term that I want to use a lot is the EOL, called end of life, RUL, called remaining useful life. Meaning from the start of today, this is the starting of the machine, and this is the time you fail, then this is your life cycle, which is called end of life. And then from today to the end of life is called the remaining useful life. So TRUL is the remaining useful life, TEOL is the end of life, TK is the current life. So it's very simple mathematics here, right? So starting from initial day, your life will be end of life. If the machine lived 1 day, then your end of life will be reduced by 1, right? So that at the end of life, that's your life. So that I know the solution. If I know the end of life, then this blue line is my solution of the problem. I want to predict that blue line as close as possible. Due to the uncertainty, my prediction will be some area associated with it, but that's the, so I'm solving the problem that I know the solution. So in that sense, I'm having more simpler problem that I have. So prognostics in my application is to predict the future behavior of degradation and predict the remaining useful life of the system based on measured data up to the current. So this is what I want to do. There are some methods to do that. The first one is called physics-based approaches, meaning I have some physical model or physical knowledge about the behavior of the degradation. It's not the system model. We have a lot of model of how the system behaves. That's your normally the system model. This is called the degradation model, how my system will degrade over time. So physics-based approaches, and then there are also called the data-driven approaches, prediction based on trend of data. If your system is too complicated, if you don't have a good model to describe it, then you have to rely on the data-driven method. So that the machine learning, AI, you heard about it, these are all, in my perspective, called the data-driven approach. The difference, whether you have a physical model to describe the behavior or not, that's the category of whether you can use a physics-based or data-driven method. Availability of the field operating conditions. Whenever we say data, we often measure the data of the measurement. But actually, the more important data is the operating condition, meaning the data in the input condition. If you are working on the experimental field, experimentalists often pay attention to measure your outcome, but you don't measure income, inputs. So if you don't know the data in the input, then the measurement of the output does not make much sense. So it's very important that you need to measure, whenever you experiment, you need to measure your input condition as well. And the damage degradation data from other systems, similar but not the same issue. So in your perspective, what do you think? The physics-based versus data-driven, which one will be easier for you to predict your future behavior of the system? Obviously, the physics-based model is much easier, right? If you have a model. The question is, what if your model is not good? Then you have to rely on the data-driven. So these are some pros and cons of a physics-based and data-driven approach. One is easier if you have it, but the other one is more complicated. But when you don't have a physical model, then that's the only way that you can solve the problem. For the physics-based prognostic method, I'm taking an example of the fatigue crack growth model by Harris and Evdon. So basically, A is a crack size. We are not in the solid mechanics. Then N is the number of cycles. So this is the basically the rate of the damage, crack growth. It's proportional to your amplitude of your stress, the crack size, and then some other constants. So these are simple ordinary differential equation. So if you integrate it, then you can measure you can predict the crack size A as a function of the cycle N, apply the stress amplitude delta sigma, A0 is the initial crack size, and some material constant. So basically, you know how it will grow in the future. The only question is, do I know the constant material parameters C and M correctly? Do I know what's the my initial crack size A0? Do I know how much stress that I apply? These are some information that you need to provide. But once you have a model, then it's pretty much easy to predict. So, in physics-based prognostics, the most important step is to estimating the parameters. So, C and M are, for example, material parameters. So, how accurately you estimate them will determine how accurate your prediction is. It's all about parameter estimation problem. Data-driven, let's think about it, data-driven. You don't have a model, right? You don't know how it grows, how it behaves. So let's say you have about this many data here. Okay. Predicting the future without having model, think about it. This could be one solution, right? But this could be another solution. You don't have a model. You don't know what will happen in the future, right? So the challenge of the data-driven method is, I know very well up to today, but I don't know what will happen tomorrow. Think about you are investing your money to the stock market. You have a good history of the stock until today. If you know what will happen in tomorrow or next week or next month, you can be rich very easily. This is the problem that we're talking about. You don't have a model, meaning you don't know how the stock will go in the future. You need to invest your money. How can you do it? If you go to your consultant of your stock investment, they say, okay, the last year, based on the economic situations, you go up or down. That's basically what it is. The other airplane behaves like this, or some other plane behaves like this. So your plane may behave like this. But basically, the similarity of the behavior, that's all about the data-driven method. In my term, it's called extrapolations. So most of the challenge in engineering prediction is all about extrapolation. If you ask me to predict what will happen between data, then I can be good. But if you ask me to predict what will happen beyond your data point, it will be really messy process. All challenges, all errors, everything is associated with all extrapolation. And then how I can describe the challenge of the extrapolation, I describe it in the form of the uncertainty. Okay, so uncertainty meaning probability distributions, right? Here we need to separate a little bit different storm. Randomness is different from uncertainty. Randomness means it's random. Uncertainty meaning the answer may be one answer, just one answer, but I just don't know. It's uncertain. It's not random. The answer will be one, but simply I don't know it, so it's uncertain. Whereas in random means every time you take the sample, it will be different. So that's a randomness aleatory. Uncertainty is called epistemic. So let's talk about it. Let's say your uncertainty is this. What would you do? To be safe. Everybody wants to be safe, right? So I cut the threshold and then say, this is my probability of failing or losing my money in the stock market. Okay, then you need to reduce this one, right? If you are a very conservative person, then probably your threshold will be much less so that your area left to your threshold will be small. That's conservative. If you are a very challenging person, then you probably take a mean or probably high end so that you expect that your return of your investment is much higher than the normal. So this kind of behavior, you choose the threshold, you make your design based on threshold. It's called living with uncertainty. I know there is uncertainty and I will live with it. Meaning I will make my decision in a conservative way so that I control my probability of failure less than the threshold that I have. On the other hand, on the right-hand side, you have the same amount of uncertainty. How about I shape the uncertainty? I don't want to change my threshold. Instead, I change the distributions. Then the area under here can be the same, meaning I can manage the same level of the probability. Either you can live with it by taking the conservative estimate, or you can shape the uncertainty. How people do this, and I do this. That's the only difference. We try to manage the same level of uncertainty. Without the shaping uncertainty, prediction may not be useful due to too large uncertainty. Your uncertainty is huge. If you take a conservative, meaning if you take the all uncertainty considered in your airplane design, then your airplane may be in the size of the tank. It cannot fly. But the only way you can fly the airplane is you reduce the uncertainty so that it can reduce the weight so that it can fly. So this is, in my terms, called uncertainty reduction. How we reduce it, that's the key question. Improve the knowledge. To reduce the uncertainty, you need to improve your model. If your model is not good, then that's something that you need to work on it. Or you collect more data. So that in my view is, how can I use my data to reduce the uncertainty? That's the key point of managing the epistemic uncertainty. So then in the regard, how many data do we need? The more the better, yes. The data is expensive, so you need to make sure that exactly how many data is enough, and what's the value of each data. And how to integrate the domain knowledge. If your physical model is some physics information, then you can utilize that one to improve your knowledge, meaning that's equivalent to the reduced uncertainty. Too many terms of uncertainty, right? This is the only two things that I want you to remember. One is aleatory uncertainty, and one is epistemic uncertainty. This one, you need to live with it. There's nothing you can do about it. You should deal with it. You need to take the conservative estimate if that's the uncertainty that you have. Epistemic uncertainty is something you can handle, you can manage it, you can change it, you can shape it. But I will focus on how to reduce the epistemic uncertainty. These are all uncertainty making part together, so they merge together. Now, what can I do is, my role is I separate uncertainty based on their source. If there is aleatory uncertainty, I will take a conservative prediction. If there is epistemic uncertainty, I will try to reduce it. So what kind of aleatoric uncertainty? This is a randomness, basically. If you take the experiment sample, every time you do the experiment, they will all change. No matter how many data that you collected, your uncertainty, aleatoric uncertainty will remain the same. That's basically the variability of your process. Epistemic uncertainty, on the other hand, is, think about, I just talked about the extrapolation, right? So you measure data up to here, and if you want to predict what will happen in the future, your uncertainty is gradually increase. So this is the uncertainty that I cannot handle it as it is. So if I collect more data, that uncertainty can be reduced. So this is more nature of the data-dependent uncertainty. This is data-independent uncertainty. So what kind of uncertainty am I talking about? I take the example of the machine learning. So uncertainty in the data-driven method. Parameter uncertainty. This is epistemic, meaning that we all know that in the training, depending on how many nodes and how many layers do we have, you have a weight and bias at every connections. So that the epistemic uncertainty means the value of weight and bias you need to determine. That determination process, we have an epistemic uncertainty. How accurate your determination of those parameters. Training uncertainty is uncertainty in construction of training and validation data. If we have 100 data, you don't use them all training, right? You use some of them as training, and some of them use a test, and some of them use a validation. How you choose it, it's random. So if you actually run the neural network in the MATLAB, for example, you repeat it, your result will be same or different. If you have the same data set, you run the neural network multiple times, will your prediction be the same or different? Unfortunately, they are different. Because you choose the random set of training, and also your optimization of the training process is nothing but the minimizing the mean square error. And that error is not global minimum, it's actually local minimum, if you know the optimization theory, so that every time you do it, you have a different result. That's the training uncertainty. Also, there are model structure uncertainty. How to define your model, how many hidden layers, hidden nodes, how many input nodes, etc. How you design your network structure has also uncertainty. But these are not nature of the randomness. These are something that depends on how you utilize your data. So there are a lot of them are actually epistemic uncertainty. On the other hand, the variance is square. So I generate the data exactly, and then I add noise, random noise of N1 on this one. The distribution of the data, the noise is the same, but actual realization of the noise are different. There's nothing you can do about it. This is the aleatory nature. I describe what is uncertainty about, what kind of uncertainty, how am I going to with the different types of uncertainty, and we'll move on to the questions. Any clarification type questions? Okay.
I have a question.
Yes.
The main task is to predict the life cycle of the structure. My question is that can we extend the life cycle of that structure or not?
So the question is, can we extend the life cycle? Let's life cycle is 20 years. Can I extend it to the 40 years? Or I will take the example of the new power plant is 25 years. Have you seen any nuclear power plant that closed in 25 years? No. So how do we extend the 25 years to the 40 years? Recertificate. Recertificate means to check the state of each part of the machines and then make it checking the current state of the system. Airplane do the same. Most airplanes go through type A, B, or C inspection and maintenance. So that when we design the airplane, we guarantee that this airplane will stay for up to 6,000 flight cycles. But before the 6,000, we inspect it, we check it, and if the crack grows beyond the threshold, they fix it, and then say, you can fly another 3,000. So that we inspect again, 3,000, continue. That's the way we extend the life cycle. A lot of accidents in airplanes and helicopters are all related to this maintenance. Recent accident in the Iranian president is also related to the maintenance area. Any other questions? Yes.
It's very aligned with the main question. In your methodology and all this probabilistic treatment, how do you insert the repairs? Because I've seen in the probabilistic model code, for example, you have like the repair is like a decrease of the percentage, so you can decrease the damage, and with this you can mix with the cost of the failure, so you can see at which point is better to do the repair to extend the life. All of this is, have you seen something, a clever way to mix all of this with this methodology? Because it's something not very well resolved now.
So thank you for the question. That's a very interesting, important question. So how we implement this maintenance and inspection schedule to optimize the life cycle of the airplane? It is a good question. We did some research, not today, but we have a research report about it. It's called the maintenance is very expensive. Buying the airplane is less expensive to maintain the airplane for 20 years. The Type C maintenance takes about 2 weeks to 3 weeks. Not only for the maintenance cost, you don't earn money for 2 or 3 weeks, right? You lose your payload for 2 or 3 weeks. So the maintenance is a major cost issue in the airline. That's why they try to put the structural health monitoring. How they maintain for the airplane is, if you go into the airplane, you don't see the airplane mainframe. All you see is the carpet and then plastic covers. So in order to have a maintenance, you need to take them all off. And then actually go in and then check the details of the cracks. And then you fix it, you refurbish it, and then you rebuild the internal structure. This is by nature, it's a very expensive process. But airplane industry try to remove those processes by putting the sensors on the airplane and then measure the damage. They only want to maintenance for the actual damage that is dangerous. They don't want to fix everything or inspect every time. It is an important issue. Today, I only say that it is an important issue. Then, I cannot say any more detail about it, but if you go to my webpage, look for my previous publications, then it is an interesting optimization process. We're not, the issue on optimization community right now is that everybody talk about optimization in the design stage. It's not optimizing for the life cycle of the system. So that's the very important issue. Actually, you need to pay attention to it. But unfortunately, I don't have material to discuss about it. Thank you for the question, though. All right. So, in our side, computer science already say data, data, data. They have a lot of data. ChatGPT, think about it, how many data that they use to train, right? Training can be several months to come up to a good model. But in my field, have you seen many data in your applications? This is life cycle. How often times have you seen the nuclear power plant actually explode? How often do you see the airplane fall down from the sky? I don't have many data. Actually, I have very scarce data to make determinations. So that's my challenge. In my field, especially for a safety-related issue, I don't have the run-to-fail data. I mean, starting from the initial to the failure, that data is very rare because people stop it before actually they fail. So then how can I do? Data augmentation is the key issue. There are other types of data which are available called accelerated life testing. To build a system in nominal operating condition, it takes 20 years. Nobody wants to test it for 20 years. How do you know that the machine will fail in 20 years? You operate it in much severe condition to fail it much faster, 6 months, and then you project it. If this one failed in 6 months, and then it will take 20 years. So that's called accelerated life testing. These are data actually available, good data, because during the test, they put a lot of sensors, they put a lot of systems to measure it. So this data is available. How can I use this data to use the current system using data augmentation? The idea is simple. You read it, and here is what it is. In the accelerated life testing, the damage will propagate very fast, blue line. In the real life, in the nominal operating conditions, it will follow the red curve. It will grow slowly and it will fail at some point here. So, but I have this data, so how can I use this data for my current system? As it is, I cannot use it. So why don't I map this data into current data? So it's called the dynamic time warping. You know time warping, right? If you go from one Earth to the sun, it takes them several months. But if you have a warping, then you can go in a second, right? As that movie, that's exactly what we try to do here. So then now using this data, we can use the current system when we want to predict what will happen if the current nominal condition is used. So dynamic time warping is a good theory already well established. So we are not developing this theory. We use this theory to convert our data from the accelerated life testing data to the practical cases. The best way is to explain it is, I think this one. This is a pi plus 1 state to pi state. So that how can you move from one state to the other is either horizontally, or vertically, or diagonally. So that's the only three states that you can determine. How can you determine which direction the state will map from one state to the other to minimize the Euclidean distance between your target system to your reference system? So that's the very simple idea that you can show it. For example, this is the one signal of the data. This is another signal of data, and I want to try to map this data into here. And this data is written in this axis. Blue one is in the other axis. Then I need to go, if these two data are identical, then I go through 45-degree line directly. Then one data versus the other one is exactly. But now this one is slightly shifted. So some point you don't move it, some point you move it up, and some point you move it down, so that it follows the best path of how this data can be used in the red one. Once you follow this path, then they look like overlapping this much. The difference between these two data sets are minimized by shifting the time from the one data set to the other. That's the easiest way to explain the dynamic time warping. And we apply this one to the accelerated life testing data to the nominal operating condition data. So here is accelerated life testing data, blue. And the red one is the current system. And then this is the threshold here, so that I have data up to only here. then I can try to map this one into there, and then I will try to predict what will happen in the future based on the mapped blue color data. So these are reference point data from 0 to 25, and then the target data from 0 to 40, and then they go either vertical, horizontal, or diagonal, right? So they move in that direction, and I try to predict this path by the regression, linear regression. That's what it is. So it's a very simple formula to map the one data set to the other. With a 95% prediction interval. Then now you can say this is the lower bound, and this is the upper bound. The beauty of this method is I can take the lower 95 percentile line, or I can take the upper 95% line, or I can make it in between. Every possible percentile I can make it, so that I can play a lot of different paths. So that's you change the percentile by 1%. You can generate 100 possible map line, and I can figure it out which, and I use that one to predict in the future. Or let's say if you have a different set of data, let's say I have three sets of the accelerated testing. This is yellow, purple, and blue. These are three tests. And then the red one is the current one. And then I want to see which data set represents my current system the most. These are from three different systems. And then this is my current system. And I want to estimate which one follows the most close to mine. And then we can estimate it based on the root mean square error. And it turns out to be the blue one match the best to my current system, so that I can use this data, not the yellow or purple color data, to predict my behavior. So we take that's our sample case. So we take the actual data from the AFRS, the Air Force particular test data. The index with the A is accelerated live testing, and without the A is the real test. So we use the 3 as our reference, and I want to predict the target of the PODAS 6 data. So this is the system, the 3 data set that I have working with, and this is the actual one that I want to use. So the yellow one is I want to predict, and the red, blue, and purple are the available data that are available, and I want to use the data mapping, dynamic time warping, to find the best data and predict the future of my behavior. So it turns out yellow is my goal. Then you may think the purple looks the closest, but it turns out the blue one represents my yellow data closest after dynamic time warping. And if you predict it, then actually you show that the remaining useful life of the blue one, using the blue one, is closest to the exact solutions compared to the other data. So this one shows that using the dynamic time warping, different system of data can be used more accurately to predict the behavior in the future. The question is, what if I don't use the dynamic time warping? What if I use the all data together? Meaning, you can think about this way. This is a heavy machine. This is a light machine. So you have a different type of machine. You use the all data together. As people normally say, the more data, the more the better. If you use all data together versus if I find the best data set to match my mind and use that one, these are the comparison between the two. If you use the all data together, your prediction will struggle a lot because these are based on different operating conditions or different systems. They will struggle a lot. Versus if you find the correct system and using the correct dynamic time warping, then your prediction will be much accurate with less uncertainty than the other case. So summary of this part is the performance of the data-driven prognostics depends on the amount of data allowed. To overcome the data deficiency, we use the data augmentation from the accelerated live testing. And this one shows the uncertainty of earlier prediction can be reduced by using data augmentations. And then using all possible training data with the different conditions or different systems may not bring you a good performance. It's not actually the number of data that you use, it's actually the quality of data that you use. That's probably the lesson that we can draw out of this one. Before we go next topic, are there any questions? Yes.
Can we generate data using the physical model? We have a physical model that is very close to or structure. Also, can we generate data from simulation in a small scale or?
Yes. It's called synthetic data.
Sorry?
Synthetic data. You make up data. The only question that you pay attention is the generated data is different to measure the data. But in order to be more useful for data, you need to reproduce the measurement environment. So what we normally do is we generate the data from the model, and then we contaminate the data using random noise and the bias. So that the story goes, if you go to the PHN community or any other community who deal with the data, you will see a lot of this case. In general application, you have the data, you fit your model. How do you know the model is good or bad? There's no reference, right? But in order to check the accuracy or goodness of your fitting process, you start from true model, you start from true parameter of the model, and you generate the data, and then you contaminate the data by random noise. And then you forget about the true model, you forget about the true parameter. Now you can only deal with the data, and then you do whatever you want to do, and then you go back to your original model to check the accuracy of your process. That's the normal what we do. And we do also a lot of this process as well. This may be related to your question before, how often we have inspection, how often that we maintenance. A similar question, but a different perspective. Let's say I run my machine from today to the 100 days. You have an option for you can measure every day. I mean, you can measure 100 times. Each measurement costs you, let's say, $1 cheap. But let's say that is $100, right? Is it a good spend of money? That's a question. It's a very simple question in the company. They try to reduce your cost as much as possible, right? So that you can have $100, you can do 100 times of the test. That's fine. But your boss will ask you, can you reduce the number of tests? What? Can you reduce the number of measurements? How can you say? Is it 50 is okay? Or 25 is okay? Or 10 is okay? You want to reduce it, so it's less than 100, obviously, but how much is good enough? Not risking your system, not damaging your system, not hurting other people, but I want to reduce it. How much that I can reduce? And how can I reduce it? Can I do it every 10? Or every 5? Or I can have a 10 first and then no test beyond that. These are some scheduling. So in what basis, in what ground can you make your measurement or inspection schedule without risking the life of the other people? So this is a schedule for the measurement based on uncertainty reduction. Here goes. Do you remember there are two types of uncertainty? One is aleatory and the other one is epistemic. We're going back to design, right? Aleatory and epistemic. Which one you can read it, which one you can modify it? So we have a good students. So aleatory, you have to live with it. Meaning, unless you change your measurement system, unless you buy very expensive sensor, this is something that you cannot handle anymore. Whereas epistemic, you can manage it, right? The idea is very simple. You can look at it later, but so that let's say aleatory uncertainty is 1. Epistemic uncertainty is 0.5. What would you do? Well, 1 is something that you cannot handle it, right? 0.5 is less than 1, so you should ignore it. What you have to do is when the epistemic uncertainty becomes greater than 1, then you can do something to make it smaller than your aleatory. Makes sense? So that I look at it, I monitor the uncertainty, and when epistemic uncertainty is bigger than aleatory, then I interrogate it, I inspect it, or I do the maintenance to reduce that epistemic uncertainty. Because aleatory, there's nothing I can do. Then if my uncertainty is epistemic uncertainty is just smaller than aleatory, I don't do the test, I don't do the measurement. I just skip it. Only when epistemic uncertainty becomes bigger. So here is the simple graph. The blue one, epistemic. Orange one is aleatory. This graph is confusing because the aleatory is changing, right? No, it's everything is 1. Everything is 1. It's only fraction of out of the entire uncertainty. The fraction of epistemic is 20%, aleatory is 80%. Here, your aleatory is 50%, and the epistemic is 50%. And at this point, your epistemic is greater than some value, right? So I choose the threshold, then I skip the measurement if the epistemic uncertainty is less than that threshold, and I only interrogate measurement to reduce the uncertainty if it goes beyond that point. More complicated graph, this is what it is. So these are my measurement schedule. And then now I'm here, and it says my uncertainty start to increase because of the epistemic uncertainty growth. Remember, aleatory remains the same, right? Then if I measure my data point here, then uncertainty of this one will be reduced. So I will work by future time, 1 day by 1 day, and then measure estimate uncertainty. And then if the uncertainty of epistemic is greater than aleatory, then I will do the measurement. If it's smaller than aleatory, then I will skip it. It's very simple. You don't actually measure it. You pretend that you measure in the future. That's basically, in my terms, called the value of your future data. Meaning the value of your future measurement. I didn't measure yet. If I measure tomorrow, how much uncertainty will reduce? If I measure in next week, how much uncertainty will reduce? So I predict the future uncertainty and then do something about it.
Sorry to interrupt. Shouldn't that threshold be 50%? I mean, because when the epistemic uncertainty is higher than 50% the contribution, that means that it's higher than the aleatory one.
Yes.
So why isn't it that threshold?
The first one.
No, the threshold. I mean,
a threshold is something, yes. I'm just taking the case of the threshold is a 50-50. 50-50 means aleatory is this much, epistemic this much, right? The total is this much. I don't want to allow that much. If your threshold is the same as the initial aleatory, what should you do? You don't want to increase your total uncertainty greater than aleatory, then you have to measure every day. If you allow a little bit more, that's why it's a threshold. If you allow more, then you allow to increase uncertainty at a certain level. Thank you for the question. So when data should be measured to shape uncertainty, that's the one question. The key idea is called global sensitivity analysis. It's a complicated math there, but I will skip all, but I'll just give you a concept. These are input uncertainty. You have many different inputs. These are input uncertainties, and uncertainty will propagate it to get your output uncertainty. Okay, so the input uncertainty going into your system, output uncertainty. Then I segregate upper uncertainty, say, how much this one contributed to my upper uncertainty? How much this one contributed? So make a pie chart of yellow one from first, gray one from second, orange one to third, and the blue one is your aleatory uncertainty. So this is the aleatory uncertainty that I have to live with it. These are uncertainty that come from other type of epistemic uncertainty. I just segregate. Having said that, conventional notion of the globalized sensitivity analysis was developed based on random uncertainty. We extended this idea to the both aleatory and epistemic, but theoretically, I don't think they are a big difference. And then skip the inspection. The instruction is simple. We have a flow chart layer, but basically it says if the contribution of epistemic uncertainty is less than aleatory uncertainty, you skip it. This is a 50-50%. If this is a 30%, then you choose the threshold, you can make a decision whether you skip it or not. To show the example, very simple battery degradation problem. It's often modeled by exponential degradation function. And then the noise of the measurement is mean 0 and the variance sigma square. So these are degradation curve with the measurement data. As you mentioned, we used the true model and we had random noise of power. To simplify the problem, we normalize it so A equal to 1. So only point is B, I don't know. Sigma, I don't know. But when you generate the data, you know what B use, what sigma that you use. But once you generate the data, you erase your memory, so you don't know it. Now you need to figure them out. So these are true values. And then 0.3 is the threshold. So X is your state, B is your coefficient, sigma is the standard deviation of your noise, which you don't know it. So how things are working in the parameter estimation. I'm not sure whether you guys learned about the Kalman filter or particle filter and the filtering technology. So basically, this is what it is. So initially, I have some idea of the lower bound and upper bound of the parameter. And then if I get the one data point, the Z data comes in, and I filter it to change the distribution into the more narrower distribution. That's the value of data. And if you have more data, then this distribution will be getting narrower and narrower, meaning your knowledge about the parameter is better and better. So that's the process that I do. This is just a mathematical form of how can I incorporate this aleatory uncertainty in the process as well. But that's not the whole idea, not important idea. This is also, to do that, you need to go through a dynamic Bayesian network because data is coming every time, every day. You cannot use all data together to deal with the data. So this is your first data, you filter it. Second data, filter it. You gradually filter it. Meaning your uncertainty, epistemic uncertainty, is gradually decreased as you get the more data comes in. That's the idea. Process. Same as what I said, if epistemic uncertainty is less than the aleatory, skip it. Epistemic is greater than aleatory, then you measure it. That's what it is. So here is what it is. I have 3 data right now. That's not this vertical line, but just the left to the vertical line. And I plot the contribution of epistemic uncertainty and aleatory uncertainty. And then I choose the point that they cross together. That's a 50-50 point. And I take that as measurement. At this point, data is coming up to this much over here. And then I find the point that the epistemic and aleatory cross 50%. That's my measurement. So if you look at here, solid circles are actually measure the point. Hollow circles are the process that I skip. So that I can decide when to measure and when to skip. That's a data-driven physics-based model. We have an exponential degradation function, and we estimate the parameter B and sigma, etc. Data-driven approach. Again, I don't have a model. So you don't have a model, you don't have a model parameter to estimate. So then the question is, how much is the aleatory and how much is epistemic? That's my dilemma that I have. What we compromise is, in the Gaussian process, for example, sigma n is your noise, estimate noise. So that's your aleatory. And the denominator is the entire prediction uncertainty. So I don't know how much is the aleatory and how much is epistemic, but I can calculate the fraction of my aleatory noise versus the prediction uncertainty. So that's my contribution of aleatory, and 1 minus that one will be my epistemic contribution. So this is simply, without going parameter, I separate what I cannot handle it versus the overall uncertainty associated with it. Same flow chart. So in the data-driven, again, these are measured, and when the epistemic uncertainty go over the aleatory, then I choose the next measurement schedule. And in this case, this is the current time, and then the epistemic uncertainty is much smaller at that point. It grows in the future, and then we choose the time the next measurement. So these are, some circles are hollow, skip it. Some circles are solid, I measure it. To compare all together, this is the model-based exponential function. This is data-driven. Total data, if I measure total data 70, until the failure, if I measure data every day, that's a 70 data. So if I measure 70 data and put them all together, then my uncertainty is shown in this bar, upper and lower bounds of my uncertainty. So this is the best you can do if you measure every day. Data-driven, by training your neural network with the 70 data all together, that's the best you can do. Versus, if we use the either measure or skip it based on the level of epistemic uncertainty, you ended up 13 measurements. You skipped a lot, and then 13 measurements, and then the level of uncertainty at the end is 6. On the other hand, in the data-driven, you only measure 10, and then the level of uncertainty is 6. That's when threshold is a 50-50. Right? So I keep the and epistemic uncertainty same level, which is a threshold 50 here. Now, if I use the threshold 0, meaning I don't accept any epistemic uncertainty, you need to measure all 70 together. So depending on what level of the threshold that you use, we can actually control how many data you need to measure and when. That's the kind of data that we generate based on true model, adding random noise. Remember? Synthetic data that we have. NASA actually performed the test of the battery, and then they provide the actual test data on the internet to people use that data for the prognostics performance. We use that one to test it. The total, if you measure every data every day, that's 108 data points. And this is the model-based prognostics uncertainty associated with it. And then using the 108 data, if we use the data-driven, that's how it looks like. We achieve the same level with the 5 data in model-based, physics-based, and then data-driven, we need a little more, 54, a little bit less than about the 50% of the data to achieve the same level of uncertainty. That's how we choose the how many data and when to use to measure data to control the uncertainty, especially for the epistemic uncertainty. So, value of future, I think that's the key point. What's the value of every measurement in the future will contribute to the uncertainty of it? We use the particle filter, but you can use the other process called the Gaussian process or other filtering technology to improve your parameter estimation. Keyword is the global sensitivity analysis. How much the input uncertainty contributed to the output uncertainty, especially for aleatory contribution, epistemic contribution, by segregating the contribution of the different source of uncertainty, and then we determine when to measure, how to measure. That's for component level. In the future, we try to expand this one to the more on the system level. Systems are much more complicated because of interaction between components. We'll address that issue in the future. That's the second topic. Any questions? Measurement schedule.
For you say that you have two kind of percentage, the aleatory and the systemic.
Yes.
So the definition of an aleatory error of a noise is that the average is equal to 0. So you measure the characteristics by standard deviation.
Yes.
But with the epistemic, the average value may not be 0. So here you're assuming that it's 0, or there is a way to treat that this may not be 0.
So the question is, if the noise is a white noise, it's a mean 0, Gaussian noise, right? Mean 0 with a variance of sigma square. Epistemic uncertainty, how can I do? Unfortunately, we don't assume any particular distribution. So for example, if you come here, so this is my starting point. Depending on what information that you have, you say, I know the lower bound and upper bound of the parameter. Approximately, based on the handbook of the material reference, the lower bound and upper bound will be 0.5 to 1.5. So that's it. I do not assume any type of distribution. I do not assume mean equal to 0. I do not assume any Gaussian distribution. I study from just the lower and upper bounds. And then depending on what your measurement of noise distribution is, the filtering process will come up to not the standard form of the distribution, it will come up to the particles. So if we use the particle filter, then the distribution is represented by a set of particles. No. It's not normal distribution. So that it does not have that notion of the 0 mean.
Then that is the number of measurements you need
Yes.
for model-based or data.
Yes.
It's surprising for me that you need more for model-based than for data-driven.
Yes. This particular case. In the next pattern problem, data-driven requires 54 measurement, whereas the model-based requires only 10. So depending on another one that I noticed, if you may pay attention, is in the physics-based, model-based, you have a measurement in earlier stage. Because this is all about parameter estimation, right? So once you estimate the parameter accurately, you don't need further measurement. Whereas in the data-driven, probably it's uniform interval to measure it because it does not have a model, so you need to continue to update your function. So this case, yes, data-driven works well. But in this case, the 54 was, there is a significant difference between them. You may say so, yes. Any other questions? Second question that I want to address is how many data are good? Well, you may say the more the better, right? But think about it. I want to monitor a system, the wind turbine system. Do you know what's the business investment or investment versus return when the profit cross time is actually the time that you recover all your investment, right? Do you know when that crossing point is? 20 years. So you build the wind turbine, and you need to use 20 years to get the actual money out of it. So that's a huge investment. Right? All right. So now then, you measure data. So water tons every. You have a sampling with 1,000 hertz. Mean 1,000 data per second. And you do the math to the 20 years. How can I store it? But if your system failed in first 5 days, no, it will fail in 10 or 20 years. So what I want to do with this long, that's the question that I want to address. There are many for PhD and based on, again, another global street analysis. All my knowledge is all about epistemic versus electrical. Then I will measure it at what it is. So just an illustration purpose, my Danish grow 15 years and then grow very fast later stage. So that's the most stage. They don't grow linearly from pristine state to Danish state. A lot of time your car drives very nicely, and then you go to the dealership and they say you need to replace something. Okay, so that's the what it is. Then should I collect all this data for 15 years? And then data has its own value, right? If you want to fit this curve, if we have millions of data here, and if we have a 5 data over there, your fit, even if we have 5 data out of it, probably your regression will not affect at all because your millions of data stay. Right? So that will also bias your fitting process. So how about I only collect the data up to here and do nothing. You just measure it, data comes in, you just look at it and then throw away, throw away, throw away. And then at some point, the data goes some trends different from your nominal state, and you start pay attention. It's called the detection of the anomaly, and then you start to predict what will happen. So this is a simple idea. I don't store, I don't collect all data up to the failure. I only collect a certain stage, and if that stage is good enough, then I skip them until the data shows some abnormal behavior. The criteria of when to stop it, again, is basically depending on epistemic versus aleatoric uncertainty. I make a decision. Flow chart, data mapping, the time mapping that we talked about in the first stage, same. So now if you look at it, this is the pretty long nominal state with a lot of noise associated with it. But if I look at my aleatory uncertainty and epistemic uncertainty. So epistemic uncertainty becomes almost zero at 80 cycles. Meaning, if you measure beyond 80 cycles, you can measure it, you can try to filter it, but as I said, aleatory uncertainty, there's nothing you can do about it. Uncertainty does not reduce, it stays there. Meaning, if I start at 82 cycles, the outcome will be exactly the same if you measure 200, 500, or 1,000. So we take the simple example of amplitude is 1 until 100, and then start gradually increase beyond 100 with the noise, which is basically the data is contaminated by this trend plus random noise. And then we go through the estimation process, epistemic contributions versus aleatory contributions. If you look at this window over here, it shows that pretty much there's nothing happened beyond that point. So this is the place that you achieve the most efficiently to reduce the uncertainty. Beyond that, these are all about the aleatory uncertainty contribution. The same slide that we did the filtering process in the previous one, and then show how the aleatory uncertainty fraction increase versus how the epistemic uncertainty fraction decrease, and then effectively it becomes zero at this point. That's the data that we generated. This is actually measurement data of the cooling fan. How long do you think that you can use your cooling fan for your computer, of the computer? So again, testing the cooling fan is, we are talking about 3 to 5 years. So how can I accelerate it? We increase the temperature to the 70 Celsius. So it's pretty much very hot environment by putting the environmental chamber. Still, it didn't fail enough fast. So that we put the small bolt here, add some bolts so that unbalanced. So that when you motor rotate it, the bearing will have extra forces. So we intentionally to make it very fast, up to 600 cycles. So that's the kind of accelerated lab testing. And we, using the vibration signal, we add the health index. So this is how the health index degrades over time. And basically it failed at some point over here. We look at the time warping, and we look at the contribution of the electronic and epistemic. And then basically at this point, 80, which is over here, right? You only collect a small portion of the data to satisfy the requirement. Only 83 data is enough. Beyond that point, you don't take more information about it. So to test it, okay, so I used only 83 data and detect the anomaly in the future versus 200 data. I collected more, 300 and 400, and I used all statistical measure of the root square, kurtosis, and variance. There's nothing much difference. Meaning the data that you collect from 83 to 400 does not contribute to anything about the reducing uncertainty of your detecting the anomaly. Same for the IMS bearing test. In this case, this bearing is it's a strange bearing. It has only very short nominal state, and then beyond it starts generating some noise and vibrations, so that the it's a very early stage of the nominal state. So most of the life cycle is under nominal conditions. So you may think that this is a very trivial, but in the practical purpose, this is actually very challenging because we have too many nominal state data. And because of the too many data, it will actually prohibit to detect the anomaly in the proper way. So we propose, based on the uncertainty quantification, that how many data do you need to properly store the nominal state. And using that one, we can determine anomaly and include it in the name. So before I go to the last topic, are there any questions? Any questions? Yes.
For setting more points, more samples, you fix because one of the things we do is just to first say not only how many points, but also how much time in real time. That means that you're sampling, and then you guess, okay, at which time and how many times will be my next samples to be optimal in reducing the.
So we did that not in the sense of optimal, but in the sense of practicality. So again, as I said, the most measurement comes in the thousands of the sampling rate. So even that measuring this one takes a huge amount of data. So we don't actually continuously monitor the data. We measure 1 second every hour. So that the 1 cycle means 1 hour, but we only measure 1 second. Meaning it's already thousands of data. So 1 second over first hour, 1 second over second hour, 1 second over third hour. That's how we use the data to process. Last topic is data-driven prognostics with a low fidelity physical information. Physics information, very buzzword. So here is my starting point. In real applications, the paradox that I'm talking about is there is no high fidelity physical model in the system level in particular. If you have a good model, you solve the problem, but unfortunately, we don't have a high fidelity model for complicated system. So, meaning, since I don't have a model, I don't have a physics, so I need to deal with the data-driven method, right? In two methods. If you don't have a physical model, then you need to rely on the data-driven. But in data-driven, as I mentioned, in my application, in our application, we don't have enough training data. The airplane doesn't fall down every day. The nuclear power plant don't explode every day. So we don't have data. So we need to physics-based approach. So the physics model need the data. Data model need the physics. So that is in English terms called the rock and hard place. There's no place that you can sit on it. So with the lack of training data, data-driven approach has a sufficient training uncertainty. This is significant uncertainty is there, and how can I address them? That's the key point. So a lot of people talk about integrating. A lot of people doing the this PIN, physics involved neural networks, they use the high fidelity physical model. But the term the high fidelity is confusing me because if I have a good physics model, then I don't need to use the data-driven method, which is I have a good model, right? But the problem is my physical model is low fidelity. It's not accurate to predict what happens, but it can follow some physical trend. That's the key word. The physics model can follow the trend, but it's not reliable. Data has noise, but it's a representation of physics. So how can I combine these together to make a smarter prediction? A very simple case of if I have this is neural net, and if I have the repeat neural net, then there's the uncertainty that I said before. So this is a neural net uncertainty. But I can say this y cannot be lower than this point. This y cannot be higher than this point. Let's say somehow your physics says you cannot go below that point, you cannot go above that point if you have these two worlds of your vision. And the question is, can I control these two together to make this initial distribution without having the wall? But if I have these two constraints, then I can make a better prediction with a narrow uncertainty. The simple idea, right? Simple idea. So what you do in the training process, so-called training process of optimization is basically you minimize network of prediction y hat minus data yi, sum of square is the mean square error, and you try to minimize it. That's purely what the neural network does. What the physical knowledge can play the role is if I know the physics and I put them in a constraint. So initially it is unconstrained optimization, but now we make it constrained optimization. Does anybody know how can you convert constrained optimization to the unconstrained optimization? Thank you. So either penalty method or logarithmic. It's just a one-on-one of optimization. Just to convert it to solve it. That's what it is. The same experiment that we did before. Now what I can do is, so this is the reality. So the gray line is if you actually run the cooling pen test, then that's a health index of glucose and eventually will fail there. But that's the real data, right? But now let's say I am 250 cycles. So I only have this much data. You train the neural network, then what will happen is it will go this. Why? Because this is extrapolation. With all this data together, if you feed it, then I'm sure that you will fit very nice trend. But if you have only this much data, then the feeding of the extrapolation of the neural network will go down. And how can the health, this is a health index, right? Health can get worse every day you live life. It's very hard to get better. Unless it's a self-healing machine. Makes sense? So this is obviously what wrong feeling. violation of the physics. The physics says my health index of my big system will get worse every day. So then why don't I put the delta x, the current x minus previous x is always positive, meaning negative of the emission, negative. So I just put a very simple constraint based on physics and then training, and then see how it goes. It's not magical, complicated, partial differential type Higgs model. It's very simple that I know that my knowledge, my basic knowledge of the system is it gets worse every day. So if you train using this data, using neural network without having anything, these are your training results out of 30 times of training. As I said before, training itself has uncertainty, right? By choosing 7% of the training data and 30% of the validation, you randomly choose. That's one source of uncertainty. And the initial value of the weight and bias randomly chosen, that's another source of uncertainty. Based on the local minima, sometimes it increases, sometimes it decreases. So these are basically not different set of data, just one set of data. You run the neural net multiple times, this is what. With the constraint that I'm talking about, very simple constraint that is monotonicity, then this is what you have. I measure how much uncertainty that I can reduce it. 70 to 30%, the bisection of the data. If I don't do that, then that's my predictions. I don't have a model. I did not use a model. I purely use the data with constraint. If I have more data, then again, the beauty of the neural network is if you have a lot of data, you can better predictions, right? So once you have this many data, then now the uncertainty is much better with the neural net. This is also much better, and this is the same better. So I can measure how the uncertainty is formed as function of the data comes in. Crack growth. This is how the crack grows. The same model that we talked about before. In this case, we put the monotonicity constraint and also the curvature is a positive. So the second, and we test it with a different set of data. To see the big picture of everything, we generate first one set of data. So this is basically recurrence model. You randomly generate the data with the noise. Same model, we generate the random noise again. So this one is a different set, but the noise has the same standard deviation. So from data set 1 to 10 are all aleatory, right? Aleatory, because these are different realization of the same distribution of noise. If you feed it, then this is your remaining useful life of lower 2.5 percentile, median, upper 97.5%. So this is a 95. Now the curve becomes more complicated because I'm going to combine all these together here. So this is your aleatory uncertainty of lower bound. This is your aleatory bound of your upper bound. This is your median bound of your the lower and upper bound of your median. So these are combined aleatory and epsilon altogether. So it's really complicated graph, but I hope neural network, these are all combined together of 10 data sets. Low of lower bound, upper of upper bound, you cannot make any decision whatsoever. Uncertainty is simply too large. Whereas if you use the constraint that we talk about, monotonicity and the curvature constraint, then all no time you can make a decision. If you just run the neural network, you can get one prediction. That doesn't mean anything in terms of answer. You need to repeat it. You need to test the different sets of data. Then you will see the difference between the constraint, fixed knowledge, versus the simply using the data. So, data-driven prognostics combine the low fidelity physical information together. We're not talking about high fidelity differential equation type physics. We're talking about very simple knowledge about the system what we know. It's integrated into data-driven neural network using constraint. You use the logic to solve it. The electron and epistemic uncertainty are separated, and the effects are compared between conventional neural network versus the P. P shows the robust prognostic performance compared to the neural network. We talk about the noise in the data, but we did not talk about bias. Bias is much more complicated prediction. So hopefully we can continue that. Altogether, that's all I want to talk about it. So if you have any questions, then I would like to answer the question, not only for the P, but any other part of it. Any questions?
I have many questions, but just ask the question. This week can be extended to medical science. I will create the baseline artifact for impact. And the second one is for the self-healing material. Also, we do need to, do health management or predict the lifestyle or, health self-healing material. Do they have a life cycle or time or not?
So far, the self-healing materials didn't show any repeating behavior. All I saw is the small number, less than 5 number of the cycling, but beyond that, I didn't see anything. Very common example, it's all polymer-based. So if you actually look at the polymer, there is a effect called hysteresis effect. The rubber, you take an initial brand new rubber initial versus the second is up to several tens of the cycles, the behavior changes significantly. Beyond that point, they stabilize. Self-healing material, I don't know so far that they talk about the fatigue effect or the cycling. I didn't see about that.
Yeah, the second question.
Yes.
For medical science.
Problem over medical science. So yes, yeah, I really want to see. I stopped smoking 20 years ago, but if I continue to smoke and I like the wine, so if I continue to drink, I want to see the doctor said if you continue to this, then your life expectation is such with uncertainty plus minus 50 years. But versus plus minus 6 months. That's a significant difference. But the challenge in the medical science, we talk about only 2 or 3 parameters here, but your uncertainty, the source of input uncertainty, starting from your genomic map of your individual versus your life environment and your life behavior, there are so many factors. Really difficult to prove. For example, there are identical twins, but one died by the lung cancer, but the other one survived for 95 years. So, I mean, identical twins. So it's really, we don't understand much on the physics. So I think that's the challenge. I want to solve the medical issue versus the stock market issue. These are 2 things that I really want to solve. But again, these are the reason that it's challenging because the stock market prediction is also so many input variables. So this is simply the dimensionality issue rather than the simple physics issue.
a lot for the talk. Thanks a lot. And more than a question, is like a philosophical opinion. So you have shown that you have your component, your measurement, and you have your uncertainty, the state. Okay, if you design this way, if you design this other way, you're going to reduce the epistemic aleatority, and you can component if you redesign this.
I can have another 12 talk about it. Have you heard about the axiomatic design? Axiomatic design? Axiom-based design? Principle?
Yes.
Yeah.
The Professor Namkyo in MIT started from axiomatic design. The first axiom is independence. Meaning, if you make a system, then each component perform only one function, not multiple. Have you seen the movie Matrix? Do you remember the keymaster? His whole life is open the door for the Neo. That's one function. That's the purpose of his life, right? So all the ways of design process is axiomatic design is independence, meaning one component functions with one function for the system. Now we talk about multidisciplinary design. Right? Multidisciplinary design means a component that plays multiple roles. Simple example is if you go to home, you have a Wi-Fi at your home. So there is a router from the cable to the network, and you have a wireless modem to send you the wireless signal to. Right? So in the old days, you have one router and one modem. But now they combine it together. That's multi-functions. The router plus Wi-Fi. In older days, if the router is broken, I replace the router. If modem is broken, I replace the modem. But now, either router or modem is broken, you replace the entire combined system. That's what the multidisciplinary. That's basically make it convenient, make it multifunctional, meaning making more vulnerable. It doesn't sound convincing you. Then if you go to the space shuttle at NASA, the structure is aluminum, and then they put a tile on top of it to protect the crew compartment from the re-entry heat transfer. So the tile is the protection from the heat, and then the frame is for the structural integrity. To relaunch the vehicle, they replace about hundreds of the tile because the re-entry, some of them falling down or damaged, so they need to replace it. But hundreds out of the tens of thousands. But now the NASA come up to the idea called the integrated thermal protection system. So to make your frame the two-layer, and then in between you fill the very strong heat resistance material called something, so that the heat comes in, it protects it so it doesn't come into the crew compartment. So it's much lighter. But the problem is when something damaged, you need to replace the entire structure, not the tile alone. So the challenge of the education is how you design so that even in one component has not interdependent between them. I think that's the key point. And uncertainty-wise, it's much more complicated because they are correlated. If you take the probability class, then correlation is your nice the correlation and more vulnerable. So I think the design philosophy on that regard is to make your design in the multidisciplinary and yet independent. That's the key point. That's a very good topic, but not many people actually talk about it. Very good convincing example is in the Second World War, if the airplane is going above you, you shoot the gun. Okay? then you make a hole to the airplane, but the airplane still fly, right? But if you shoot a gun to the F-34, then probably you will not survive. It's so complicated electronic system to combine together. So if someone shoot a gun to the airplane, then probably you fall down from the sky. That's the dilemma of the multidisciplinary design. Even if it's high performance, but at the same time, it increases the overall. Hopefully that answers your question. Not too much detail.
I have one question.
Yes, sir.
Well, thank you very much for your talk. It's been really interesting, as my coworker said. Especially when we're talking about data-driven and these kind of things, we're typically connecting it to AI, machine learning, and so on, like the last part. But it's also interesting to study or to review the other parts of the global sensitivity analysis, the discussion about the different types of uncertainty. So thank you very much for that. My question is, from your experience, from your work, since this prognosis work has different stages, which is the most critical stage? Like the model, the last part of the stage, the scheduling, how do we perform the dynamic time walking, or based on your experience, which is the most critical?
Most critical part is, in my humble opinion, is about the cost.
Defining the cost function or the cost in terms of monetary cost?
The actual cost.
Okay.
The actual cost. We are scientists, engineers, so we are driven by technology, but the society is not driven by technology. Society is unfortunately driven by money. So if you look at the one of my 2019 paper about the cost effectiveness of maintenance, so the sensor-based maintenance is a really fantastic idea, isn't it? As I said, if you go to the airplane, a lot of plastic and carpet cover, you need to take them out, and then actually the technician go in to inspect it, versus you put the sensors, and you automatically measure in real time how fantastic the idea is. But then why the data airline don't put the sensors on the airplane? Any ideas? Any slight idea of close to what it is? Why is it expensive? That's the question. Why is it expensive? As I said, it's cost driven, right? Why putting the sensor is expensive? Sensor cannot be just the sensor alone. Sensor need to be connected to the system. Have you ever think about if you want to monitor the cracks on an airplane? Airplane is not simply plate. It's made out of the complicated spars, stringers, and rings. It's very, really complicated to measure the damage over the every point. How many wires do you need? Sensors are about this size, almost ignorably weak. Okay? But to connect that sensor to the outside system, you lose the payload. An airplane is caused by every payload. So that it's actually cheaper by human inspection is cheaper than sensor-based monitoring. It is important, fantastic idea, but cost-driven. Why is it expensive? Because it's the ad hoc time. Airplane is designed based on philosophy of manual inspection. They design, they change, they determine the thickness, size of the spars and stringers based on every 6,000 inspection schedule. Meaning the crack that you can, small crack will not grow dangerously until 6,000 cycles. That's why they set up the design. They make the inspection schedule every 6,000 cycles. That's a design philosophy. And then, so that the manual inspection design philosophy, you add hope to the sensor out of it, it's an additional burden. If you design your airplane based on the sensor-based inspection schedule, then it will be completely different. But that's what the design is also important, because you make a system for the one idea and then attach another one for the different purpose may not make you more efficient for the purpose. So there are, in addition to the technology, there are a lot of things that you need to take into account to make the technology to be more practical. That's why don't make your own business out of the technology. That doesn't work. I graduated from the Korea Advanced Institute of Technology and Science for my master program. And that school is famous that they about a lot of new idea comes out and people quit the school and they started their own business and then 90% income. So, because technology is only a portion of the entire picture of the business. Not a good story to tell. Any other questions? Yes.
Practice simulations on the life of the second life of component. It was assumed that it can only grow. Have you tried to introduce, like, stimulate, like material treatments in the middle, like, for example, something that could close the crack, like laser or thing or something? Have you taken that into account?
We are doing that now, actually, in this summer. So let's say you found a crack in the airplane during the inspection. What would you do? You throw the airplane? What would you do? It's called the concept called the tabula. So basically, you crack a plate. You put the there is a spec. You put the size of the plate, attach it, and then pass them around that. What does it do? It reduces your stress. Right? You cannot close the crack, unfortunately. You cannot. You cannot take off the plate. It's called a scrap. Scrap is much more expensive. So if you actually go to our department office, the table, meeting table is the airplane wing, the old wing. And if you actually look at there are a lot of tabulas attached to them. So what we try to do is, let's say your crack started, grow in somewhere middle, and you expect it'll be dangerous after 3,000 cycles. Right? Then question is, can I design my tabula in early stage so that I can control the thickness and size of the tabula so that I can extend this type to the 15,000. Basically, design purpose. Yeah.
Very interesting presentation. My question is, for example, during the validation process, we want to use the model to predict the life cycle, and the point is, when we manufacture a prototype, so when we want to test it, the point is, for example, for airplane, it can be designed for 6,000 cycles. The point is we can wait, but we don't want to measure in the first few cycles. We wanna exercise, we can wait. So sometimes we will apply some like extreme working condition. So you mentioned an algorithm to verify its fit to the how fit with the models. But for example, for the new design, probably you have no to fit the new design. So you can't you what you will do.
First part when they design the accelerated life testing. So if you apply the nominal operating condition, it go long high cycle fatigue. But if you apply too much force, then it doesn't go to the high cycle fatigue, but it goes to the low cycle fatigue. So the plus equations, you cannot increase the load by 10 times or 100 times. You need to make sure that the failure mode has to be the same. That's the first part. Car for 1999. In 2004, now you design a new car. Can I use the same the data that I collected from the 1999 car? That's the question. No. Same way. But the you can think about it throughout the engineering life, car industry, automotive industry. How many times that you actually come up to the completely new model? I would say you'll be very lucky if you anticipate in completely new model design from scratch. We never done that. It's very easy to say, but in reality, it's always based on some frame. So you design based on some frame means the frame is basically the major load carrying system. So that how the load is distributed in the car is pretty much the same. Outside look different, engine size different, your mission will be much better than before. These are all improvement, but we are not the necessarily design. We are doing mechanical design, right? How the load is distributed that cause the damage of the system in the same way. So I don't think that's completely different, even if you are talking about different model. Not only for the automotive, but even the airplane, unless you go to from the subsonic to the supersonic regime change, but the frame, the load that you receive from the wind on the hypersonic cases are pretty much the same.
Just have one comment.
Yes.
It's not only money, at the end it's money, but sometimes, I've been told once that sometimes you don't want to know because you only want to know if in the end you know you're going to make the measure to budget. Because if you know that you didn't take the measure and something happened, then you are in trouble. A lawyer will tell you, so you knew. And it's similar to the percentage of uncertainty.
So, well, since you say in the, if you remember the next phrase, the Secretary of the Defense, Donald Rumsfeld, times when the George Bush is in president. During the Iraq War, the reporters asked him the question, did you know or not? And he said, there are known unknowns and there are unknown unknowns. Have you thought about it? Known unknowns. That my mother has a parameter and it's uncertain, right? So these are known unknowns. A known unknown is, I didn't know if there is anything existing. And then what the Professor Montan says is, there is a thing that one that I don't want to know. There could be another one. A lot of engineering, especially for design area, is about responsibility. Conservativeness is all about the responsibility system. But that calls also the inequity. If you go to the Armstrong, they make the gas turbine engine. This gas turbine engine is very expensive in a sense. If you start one day, you lose $1 million. And then you don't have a switch that turn on and off. We have enough electricity, that's turn off. We need more electricity, that's turn on. No, it's not working like that. To start engine, to go to the full cycle, it takes 2 weeks. You start from low cycle, gradually increase the RPM, and the full cycle 2 weeks. You start one day for maintenance, it costs you about $1 million. You don't generate electricity. So do you know when they start the engine? They come to me and complain that my design department says you break you need to have a maintenance in 6 months. So they stop it in 6 months, they go into the machine, there's nothing wrong. When they run the 6 months again, they stop it, they go in, they check it, nothing wrong. And they come back to the design department and say, you guys are lousy. How do you predict that the machine will be better in 6 months? But I used it 1 year, there's no fail at all. You know why that happened? Because design is all about conservative. We don't want to fail. We're not talking about mean over the failure. We're talking about 97.5% of the failure. And when they actually stop the machine? When the insurance company says so. Again, cost driven. So a lot of decisions are not driven by technology or the design. Unfortunately. Any other comments or questions? I know sitting 2 hours is very hard. Thank you very much for sitting for a long time.
Thank you very much for your time. And I think that but I know that we make a break already. We make a complete break. So, is there any question for the internet or not?
Sorry?
Is there any question for internet?
No questions.
Okay, so we can go to the second part. Will be brief. So basically, I wanted also to take the opportunity that he here and he's from the US. So he can explain a little how the. I know for me it's very. I know it, how it works, but some of you don't know exactly how the system training works and what the students usually do, and also, I mean, what the type of opportunities for doing postdocs and fundings and all of that kind of thing. But graduate students can take advantage of it. So thank you very much. If you want to talk a little about that. Sorry.
Could you close the
Yeah, sure.
PowerPoint and
Is there another presentation?
Yeah, another one.
Okay. Sure.
And close it, and that is called the joint PhD lab.
Okay, perfect.
In the program.
I joined.
Yes. So PhD program, I cannot summarize the PhD program because I can answer questions because it's so broad, what we're interested in. But the one that I'm interested, I've been very successful about it, was called dual degree PhD. 10 years ago, it's called a joint PhD, but now it's called a dual degree program. And then I've been about 6 or 7 joint or dual degree programs with different countries, including academia in France, and also in some universities in Korea, and also in Argentina. So probably this might be a good opportunity to you guys to think about it. So students satisfy almost all requirements for PhD at each institution. So the UPN and the UF. That sounds very tough, right? Which part do you think is tough to satisfy both? I mean, having the 2 PhD, you get the 2 PhD of UPN and the PhD of the UF. What if I say you need only one qualified exam and one defense and only 10% more coursework and getting the 2 degree. So how it works is single dissertation jointly awarded. So even if you, meaning that we satisfy both institutions' requirement, but you need to write one dissertation. That's a good part, right? Bad part is one or more advisors eligibles. So having 2 advisors is probably taking the part because they may have a different ways to guide you. Normally, how we do is that we consider PhD degrees of 4 years. So you spend 2 years in one institute and then 2 years in another institute. How about the coursework? You take the course at UPM and it can be transferred to the UF. If you take the course at UF, it will transfer to the UPM. So you don't need to take the much extra coursework. I don't know how the tuition and the financial help comes in UPM, but in the US system, not only for the US, but most US system, PhD students' tuition is paid by advisor, and then the monthly paycheck is paid by the advisor as well. So that the only small amount of the cost you need to pay to the university, including the insurance, but 35K. UF students get about 35K per year for PhD students. So that's the how the cost comes in. And the PhD depends in one country, either UF or UPM, and then the other committee on the other side will join by teleconference. Right now it's a good view because it's only 6-hour difference. So if we have a presentation in the morning at the UF, it will be afternoon in the UPM, so it's doable. When I was doing the Korea, they have a 12-hour difference. So I need to ask some committee to stay late in the evening. Cost transfer is more liberal, so that's the benefit side is the students get benefit for guidance. So not only for single advisor, but the joint advising will give you more networking and then official degree from both schools. International background is very useful for cultural purpose, but also your experience. One experience that I want to say is from the Vice President of Prof. So I talked with him. Prof sells their car a lot of countries. You think they make one car and sell different countries? No, they make different cars for different countries. Why? Because different country has different regulations, rules, requirements, etc. So basically, even if they sell Ford Taurus or Ford Mustang, their Mustang in US is different from their Mustang in Australia, their Mustang in Brazil, they're all different Mustangs. Then, if you want to sell a car to that country, you need to understand how people work, how people think, how people behave in the country. So one of his experience was when he went to the Prof in Japan. In the morning, there were 6-year-old kids wearing old yellow dress with a yellow hat and a yellow backpack. Okay? And then coming out from one house and then going to the next house and stay there. Then the second kid from that house come out, they make the line, and go to the next, and they make line. So they make the line until they reach the school. It's I never saw that one, but he saw that one in Japan for long time ago. And there was a huge difference in culture between US and Japan. And he told me, without understanding their culture, how am I going to sell a car on the country? That's basically baseline of the background is really important. When I come here, first time in Spain, in the restaurant, I realized that people talk really a lot. Wow, the amount of the conversation within the table is at least 3 or There are a lot of international collaborative research funds from the NSF in the US, and also I'm sure that we have some foundation, research foundation in the Spain as well. Compromise on research. Dear Professor, I'm clearly selfish, I love money, and I try to control everything by myself because the knowledge is very different from the human communication. That's why probably the professors are not social people. They are more eccentric because they go into their idea deeper and deeper. Sometimes it's good, but sometimes it's good to talk in depth with other researcher to make a conversation to smooth out the horns of our research. I think this is a problem. 6 hour difference, it's a morning and afternoon time, so that the meeting together, in a lot of time, I need to wake up and then sit in front of a computer at 10 p.m. Bureaucracy is really sometimes difficult. One student I have is, in order to get approved for dual degree program, I need to go past the graduate council. There are 8 members in the UF, and sometimes people are picky and some paperwork that I need, but that can be done sometimes. Some chat over my other professors. A students, then I need to send a student unit, A student assistants that I need to earn the money. Let's say each students have 3 publications, I have 24. That's their baseline. If I have a student to join the PhD, then the money that I pay is about 4 assistants, right? I don't pay 8 students, half of the 8 students, so 4 students. About time, a little more than the normal students, so let's say 5. Publication to 8, 24, and credit, the same credit, same publication. General, maybe not 24 because it's a co-authorship, right? It's not just me and students, but overall, to me, it's a buy one, get one free. Spend only half of my budget to advising. I'm the main advisor, and other professors co-advisor, and then advise students together. I'm mostly on the simulation person, computer programming. Support team from Korea Aerospace University with Professor Chuo Choi and me, and he got the master in 2018 from Korea Aerospace University, and the PhD. He published 17 papers. Because the synergy effect, and then 4 patents, and then 1 patent was sold out last year. You know what do you mean by the patent was sold out? Some company bought that patent from the university. Some award. So my dual degree joint PhD students were very successful. Partly because the student was excellent, so that the professor wanted to work with it together. Probably that's the part of the reason. But in my experience, another students wrote a book with me, so that's very successful as well. These are all good memories. UPenn, we have about 40,000 students. UF, we have about 50,000 undergraduate students. So it's a big university. So we have basically any field that you are looking for, we have it. Starting from hospital to the liberal arts, law, agricultural, you name it. Any department that you heard about, you have to have it. So it's much easier to collaborate in the different areas of engineering, science, medicine, and agriculture, etc. So the collaboration, we have very good facilities in terms of the material testing, high performance computing, also in the different areas of the medical research type facilities that we have. UF is very proud recently. I don't know why, but the number 6 in the best university in the US, public university in US news report. So that's our ranking system increased recently very fast. So the university put a lot of effort on the research and the education. That's the other area that you may think about applying for the UF. The largest department, our department, Mechanical and Aerospace Engineering, is the largest department. We have a mechanical engineering, the aerospace and science engineering programs. We have about 55 tenured and tenured faculty. We are going to go more than 60 plus, and then some numbers that we So yes, we emphasized recently a lot about the space education. Florida is a nearly NASA facility, so we have a lot of the space type application and the environment opportunity as well. So that's what I prepare for the dual degree PhD program. But in general, if you think about studying US, then the question that you I don't think you're students though, right? Go ahead.
Who do you call a good student? What's your criteria to call a student to be good?
In different professors have different expectations, right?
What are yours?
I want independent students with independence. So, no, I misunderstood this question. So, who the student I was?
So for example, you have there are some applicants want to work with you, and there are some series. I mean, who would you consider to be your student?
Oh, yeah.
Based on your
Good question. Good question. It's a very practical, Professor. Normally, I receive about 100 emails from the students, future students. Look at their CV and resume. What do you think? Do you think that I can find a good student out of it? I tried for 20 years, but I'm miserably failed. In the resume, I thought this is the best students, but students who, you know what mean of all the research, meaning it's not my professor's research, this is my research. I want to do this. That ownership is the I think, very important attitude of the successful student. Any other questions? Everybody's hungry.
That's one. Sorry, I came in. In your case, you are applying your field to different topics. So how important is to do the research in one topic? I will find in a postgraduate.
So I don't do research in my PhD topic anymore. On the history, I changed my topic 3 or 4 times. For example, when I was a PhD student, I was a computer programmer. I'm solid mechanics people. I write the nonlinear finite element code using machinist method. And I use the Fortran, and I believe I write about 45,000 lines of the code. I'm very proud of it, but I don't do research for that one. So it gradually moved to different places because of the different interests. That's maybe probably the best part of the staying in academia. I worked for defense industry for 5 years before I come to the US for the study. The one that I hate most is I have to work something that I don't think is important, is necessary type things, because it has to be higher structure. But in school, you can determine what you want to do, as long as you take the responsibility of them. The freedom, the responsibility always go together. But so I moved to the more on the reliability design, and then prognostics and health management, and then verification, validation, and uncertainty quantification. So I have some pro of history of this study, but the bottom line, the foundation of my research is all about the managing the uncertainty. So that is some backbone, but the application of the research flows different areas based on time, based on interest, based on how the people demand.
Basically, I think that what you meant is that you usually do research in one field, but then you follow the golden rule. And the golden rule is who has the gold make the rules. So basically, where the money comes, you just. I wanted also to, for him also to explain with, because he's actually doing a double PhD, also with Ensan, so he's VPN and Ensan. So on top of it, but yes, you can actually already this. So let's thank him.
Okay, yes, I wanted to add some things from the other side. Okay, I wanted to add some things. My experience with the European side of this kind of agreements. Yeah, that is how we know me. I'm Luis de la Torta. I'm part of the Executive project, like the guys you see in front. And well, the advantages have already been said. I was working. I think it's a win-win situation. Everyone gets a reward from this kind of agreements. It's, at least in my experience, it has not meant extra work. Work is the same. The only thing is you can collaborate with supervisors or more. Usually their topics are related, so you don't have to stray away from your main research line. And considering we work in the same project, it's obvious that if we exchange with partner institutions, our topics will be related. So that's a problem we don't have to deal with. And about UPM, I can talk about the process a bit. So you know, you have to take 3 steps. One of them, you have to fill in the co-supervision form they have in the UPM website. There's a version in English and a version in Spanish. Usually it's better to tell it in English because the institution may not speak Spanish. And there are several annexes. The first one is the agreement itself. It has to be signed, I think, by the rector, or the dean, or the equivalent position in the other institution. And there are several agreements depending on whether if the institution has already an agreement with the other one or not. But it doesn't take much time. The signatures could take longer, but it's not a lot of work. The other thing you have to do is through the thesis platform, you have to register the other co-supervisor of the invited institution as a European researcher. So that could take longer. If they ask you for their CV, you have to fill in like several data checks, like publications and stuff. It doesn't take very long. And then when all of that is signed, the first step is to ask for the eco supervision itself. When he's registered, he or she is registered in the platform. Through thesis, UPM, you have to ask for the eco supervision to admit him or her as a co-director. And then the CPAD, the doctoral committee, has to approve that. And that's pretty much all. It's easier said than done because it could take long, especially if it's a new agreement. But I think we paved the way for that. So I encourage you to try. I think it's really worth it. And it's, I think the advantages outnumber the disadvantages. So that's it.
Thank you very much. Thank you very much, everyone, for coming. Thank you very much for long calls and so thank you.